Blast cold air into molten iron. Logic says it should cool down. Instead, it got hotter, much hotter. That strange reaction turned ordinary iron into something entirely new. Steel, made cheaply, made fast, made at massive scale. One converter, one surprising discovery. An entire industrial empire followed. Quick question, before we dive in, where are you watching from today? Nobody expected cold air to make metal hotter. That single surprise changed how the entire world built things. Steel existed long before the 1850s. It just wasn't practical for much of anything large. Producing it required slow, expensive methods, working small batches at a time inside crucible furnaces. Making enough steel for something massive, like railroad tracks or ship hulls, simply wasn't realistic. Iron filled that gap instead. Cheaper, more available, workable at genuine industrial scale. Iron carried real weaknesses, though. It bent under heavy loads. It wore down quickly under repeated stress. Railroad tracks made from iron needed constant replacement, sometimes within just a couple years of installation. England found itself needing better metal for an entirely different reason during this period. The Crimean War had exposed serious weaknesses in military equipment, weaknesses that cost soldiers their lives. Henry Bessemer, an English inventor already known for various mechanical innovations, got pulled into this problem directly. In 1854, he met with Napoleon III, France's emperor, who wanted improved cannon technology for his own military. Steel seemed like the obvious answer for stronger, more reliable cannons. Existing steel production methods, though, made large-scale manufacturing essentially impossible. You simply couldn't produce enough steel, quickly enough, or cheaply enough to outfit an entire military. Bessemer recognized something important in this challenge. Solving the military's cannon problem might also solve a much bigger, more valuable question: how to manufacture large quantities of steel affordably. By 1855, he'd shifted his full attention toward exactly this goal. Rather than simply improving existing slow methods, he wanted something fundamentally different, a process capable of converting raw iron into quality steel quickly and in genuinely large batches. This ambition extended well beyond military applications. Bessemer understood that affordable, mass-produced steel could transform far more than weaponry. Construction projects throughout Britain and beyond desperately needed stronger materials. Railroads expanding rapidly across multiple continents needed track that wouldn't wear out within a few short years. Bridges, buildings, machinery, all of it could benefit enormously from steel strong enough and cheap enough to actually use at scale. Nobody had figured out how to bridge this gap yet, though. Steel remained a specialty material valued for its strength but priced far beyond practical use for most large-scale applications. Bessemer began experimenting throughout 1855, searching for a method that could finally close this gap between steel's obvious advantages and its impractical cost. What he eventually discovered wouldn't just fix cannon manufacturing. It would fundamentally reshape how the entire industrialized world approached construction, transportation, and manufacturing for generations afterward. Bessemer wasn't trying to reinvent construction. He was just trying to build a better cannon. Bessemer's breakthrough came from a genuinely counterintuitive idea. Molten pig iron contains various impurities, carbon and silicon among them. These impurities make iron relatively weak and brittle compared to properly refined steel. Bessemer's insight involved blowing compressed air directly through this molten iron. On the surface, this seems like it should cool the liquid metal down, introducing cold air into something extremely hot. The actual chemistry worked completely differently, though. Oxygen within that blown air reacted directly with carbon and silicon impurities present in the molten iron. This reaction happened quickly, and it released substantial heat as a byproduct. Rather than cooling the metal, the reaction generated enough additional heat to keep everything molten, sometimes even increasing temperature throughout the process. Impurities converted into oxides during this reaction, separating out as slag that could be removed from the purified metal. What remained behind was something much closer to genuine steel. This entire transformation happened remarkably fast too, compared to traditional steelmaking methods. Where older processes might require hours or days working small batches, Bessemer's approach could process substantial quantities of iron into steel within roughly 20 minutes. Bessemer filed his first patent for this process in October 1855. He officially secured full patent protection the following year in 1856. That August, he presented his findings publicly for the first time, delivering a paper titled "The Manufacture of Malleable Iron and Steel Without Fuel" before the British Association meeting in Cheltenham. If you're finding this story fascinating, hit subscribe. We cover engineering breakthroughs like this every week. News of Bessemer's presentation spread quickly throughout Britain's industrial circles. The Times newspaper published his complete findings, ensuring widespread attention from iron and steel manufacturers across the country. Reactions split fairly dramatically between genuine enthusiasm and considerable skepticism. Some manufacturers immediately recognized potential for genuinely transformative change throughout their industry. Others remained doubtful, wondering whether this seemingly too good to be true process could actually deliver reliable results at commercial scale. Bessemer moved forward regardless, licensing his process to interested manufacturers eager to test this revolutionary new approach for themselves. What happened next would reveal something important about invention versus practical implementation. Having a brilliant underlying concept, it turned out, represented only part of what was actually needed to transform an entire industry. The idea was brilliant. Turning it into something that actually worked reliably was a completely different problem. Bessemer licensed his revolutionary process to 4 different manufacturing companies, collecting roughly £27,000 in licensing fees from eager early adopters. Excitement quickly turned toward disappointment, though. Steel produced using these initial licensed operations came out brittle, unreliable, and genuinely unsuitable for the demanding applications everyone had originally envisioned. This created a serious problem for Bessemer's credibility. His underlying scientific concept was sound, clearly demonstrated through his own experiments. Something was clearly going wrong, though, when other manufacturers attempted replicating his results at genuine commercial scale. The core issue involved carbon content specifically. Bessemer's air-blowing process removed carbon extremely effectively, sometimes too effectively, leaving finished steel without enough carbon to achieve proper strength and workability. Solving this problem required additional insight beyond Bessemer's original breakthrough. That crucial insight came from a considerably less famous figure, a metallurgist named Robert Forrester Marchette. Marchette discovered that adding a specific alloy back into the process after the initial air-blowing stage could solve this carbon deficiency problem directly. His solution involved a compound called spiegelisen, containing carefully balanced amounts of iron, carbon, and manganese. Adding this alloy back into the mix restored proper carbon content within the finished steel. Manganese present in this mixture also helped to neutralize sulfur, another impurity that had been causing quality problems throughout Bessemer's original process. This additional step transformed Bessemer's promising but unreliable concept into something genuinely production-ready. Steel produced using this improved combined process finally matched the quality and consistency manufacturers actually needed for serious industrial applications. Marchette's crucial contribution rarely receives equal recognition alongside Bessemer's more famous name, despite genuinely making the entire process commercially viable. Without this specific fix, Bessemer's original breakthrough might have remained a fascinating but impractical scientific curiosity. Adding further complexity to this story, an American ironworker named William Kelly had been conducting remarkably similar experiments years earlier, starting around 1847 near Pittsburgh. Kelly theorized independently that blowing air through molten iron could achieve comparable results. Kelly didn't secure his own patent until 1857, a full year after Bessemer's official patent. Questions persist even today regarding exactly how independently these two inventors actually arrived at such strikingly similar solutions. Whatever the true relationship between these parallel discoveries, credit historically settled primarily on Bessemer's name, while both Marchette's crucial fix and Kelly's earlier parallel work received considerably less recognition throughout popular history. With Marchette's carbon restoration solution finally solving the reliability problem, Bessemer's process could finally deliver consistent, genuinely usable steel at meaningful commercial scale. One significant limitation remained, though, and it threatened to restrict this breakthrough technology's broader global impact. The process finally worked, but it only worked on one very specific kind of iron ore, and most of the world's ore didn't qualify. One surprising reaction, two overlooked fixes, and a converter that turned cheap iron into the backbone of the modern skyline, even after the machine itself was retired. The empire it built still stands today. If you enjoyed this story, hit subscribe for more industrial history.